Alright gang, here we go. This is for Chem 1 Unit 14, Part 1. We're talking about equilibrium. This stuff's pretty fascinating. It's kind of wrap up a lot of things that we've talked about over the years. You're gonna have to really stretch yourself a little bit to finish it up. Anyway, so let's talk about it real quick. First time we talked about equilibrium, we talked about the idea where if we had a beaker that was full of water, okay, this water, if you just left it out in a room, this water would eventually evaporate, right? It would turn into water vapor and it would just kind of float away, and eventually all the water would be gone. Then we talked about, well, what if you have that and then instead of just open to the air, you put a lid on it? Well, we talked about how this water would evaporate and it would create water molecules up here, right? These water vapors would come up here, but at the same time, these water vapor would be bouncing around and they could heat each other and slow down. And if they slowed down enough, they would recondense, right? And they'd fall back down into the water and form liquid water again. And then the liquid water would evaporate to replace it, so on and so forth. And eventually you'd reach a point in time where your water would be evaporating just as quickly as the water is condensing, right? And so if it's evaporating just as fast as it's condensing, it gets into this cycle, and we call that equilibrium. Specifically, we call that dynamic equilibrium, because the dynamic, remember, dynamics means change, and so it's still changing, right? Our reaction, it did not stop evaporating and it did not stop condensing, but the relative amounts have not changed. So we call that dynamic equilibrium. Now, another thing that we've really kind of not talked about a lot, we briefly mentioned it a couple units ago. We talked about how almost every reaction is reversible. Okay, our reactions can go forwards, right, from reactants to products like we've kind of established in the past, or they can go from products to reactants, right? And so here would be a chemical equation here. Notice that we've got this double-headed arrow right here. This is saying that our sulfur dioxide can react with our oxygen to form the sulfur trioxide. You know, reactants can turn into products, but at the same time, our products can go backwards and turn into the reactants. And you can see in these different pictures here, you've got, your sulfur dioxide that's not at equilibrium, and then sulfur trioxide that's not at equilibrium, and then the two can meet, and you can have a mixture of both. Here's some sulfur dioxide, here's some oxygen, and here's sulfur trioxide. Okay, so this is what we would call these guys. So if we're looking at our reaction that's going like we're used to, we call that the forward reaction. All right, that's the forward reaction because it's going forward. And then the reaction that's going backwards, we call that the reverse reaction. All right, and I don't know why these arrows are crooked. All of a sudden, I swear they weren't crooked just a second ago. Or maybe they were and I'm just dumb. All right, let's see. All right, you just saw behind the curtain a little bit. All right. So anyway, and so we get this reaction that's going from both to both. Right? It's a reversible reaction. Now, here's a bunch of important things that you need to know about a chemical equilibrium. Number one, it can only occur in a closed system. Think about that beaker example we talked about at the very beginning. You would not reach that equilibrium between condensation and evaporation if the lid was not on that. The lid kept it closed. You know, if it wasn't closed, then that water would just keep escaping. So so what does it mean to be a closed system? Essentially, that means that whatever a reactant, when it turns into a product, it needs to stay and be able to react with itself to turn back into a reactant or whatever else is there that it needs to react with. And so, like, if you have only aqueous things, essentially they just need to stay in the beaker. If you have gases, then you need to put a lid on it just so the gases can keep reacting, etc. All right. Another big thing about equilibrium is that once you've reached your chemical equilibrium, there is no net change that occurs in the amounts of each component in the system. You're going to have the same amount as soon as you've reached equilibrium. Your relative amounts, or the ratio of reactants to products, does not change. All right, that ratio. So it does not mean that you have equal amounts of both. What it means is that you have no net change in the amounts as they go. All right, remember, these reactions keep going. They haven't stopped. Okay, they're, if reactants run into each other with enough energy and the right orientation, they can still react and form products, and the products can still, react by collision theory and to form reactants. So the reactions keep going. They go both forwards and reverse the whole time. Okay, but remember, it does not mean that the concentration of the reactants and the products are the same. You could have, depending on whatever your reaction is, you could have way more products than reactants. Okay, so a classic example here is like if you take water or hydrogen, okay, and you're going to burn it. Say you got a hydrogen balloon, you're going to burn it with oxygen, right? This would be a reversible reaction, and this would form water, right? This is the why did I write a plus? A 2 for water, right? And so this hydrogen would react with oxygen. We've done this in class, and you felt how the heat coming off of it, and there's very, very little hydrogen left. But this reaches equilibrium. Our classroom would be a closed system, and so, but we know for the most part, we just have water vapor that gets formed. Very, very, very little hydrogen is left. So it's reached equilibrium. However, these relative concentrations, obviously, we favor heavily the water side. Okay. So here's a couple of graphs to help us kind of visualize what's going on. This top one, we're looking at rates. Okay, now remember in our beaker example, we were talking about how we reached equilibrium when the rate of condensation was equal to the rate of evaporation. Okay, and so this is the same idea. We've got our reaction here, the forward versus the reverse rate. At the very start, this is we have our forward rate is way faster than our reverse rate. It looks like our reverse rate is completely zero. So that implies that we had only reactants when we started our reaction and no products when we started our reaction. Okay, and so as our reaction goes, we run out of reactants. They're turning into products. So the forward rate is slowing down, but the reverse rate is speeding up. And eventually we reach this point right here in time where we are at equilibrium. And now that we're at equilibrium, okay, our rates are now equal to one another. Our reactants are turning into products just as fast as our products are turning into reactants. All right, down here, the second one, now we're looking, instead of rates, we're looking at amounts. Remember that at equilibrium, our amounts are not necessarily equal to one another. They can be, but more times than not, they are not equal to each other. All right, so our reactants, we have a bunch of reactants, we have no products. As time goes on, our reactants go down, and that makes sense because they're being used up, and our products amount goes up because our products are being made, right? And so eventually they level off, so that once we're here, we have no net change in the amounts. This ratio is constant between products and reactants. Now, we need to be able to represent all of this stuff mathematically. And so in order to do that, we're going to use this thing called the equilibrium expression. All right, so imagine you have a reaction, okay, that looks something like this. This is a generic reaction. The capital letters represent the reactants and the products, okay? So, so in our example before, we had like H2 plus O2 was in equilibrium with H2O. Okay, we could balance that. Probably should balance it. Okay, so the capital letters would be, the A or the H2, the O2, and then the H2O, that whole thing. And we would not have this D, okay, because this one only had one product. All right, the lowercase letters are the coefficients, so the A would be the 2, the B would be a 1, and that C would be a 2 right there. All right. And so the way it works is you simply take this guy and you do products over reactants, right? These are your products, all right, your products over reactants. And then you take the value or the concentration. Notice that we've got brackets. Those square brackets mean concentration and molarity. So you take the concentration of whatever component you're talking about. If it's products, they go on top. If it's reactants, they go on bottom. And you raise them to their coefficient values. So the C is raised to the lowercase c power, and the capital D is raised to the lowercase d power. So, and it's pretty simple. So if we were going to do KEQ, and the K value is your equilibrium constant. Okay, essentially it's a way of keeping track of that ratio between products and reactants, and then EQ stands for equilibrium. We'll talk about a couple of different kinds of K's as we move on. So this is our equilibrium constant. All right, and so we do products over reactants. So our product here, let's look at this this reaction we did up here. So our product here was H2O, so we'll do concentration of H2O, and we're going to square it, and that's because there's a 2 in front of it. All right, and then we will put our reactants on the bottom. And we only had one product, so we're only going to have one thing on top, and then now we have H2, and then we're going to square that guy, and then O2. Right, simple enough. All right, now the next rule, and this is a biggie that'll throw you off if you're not paying attention, you never include solids or liquids, so you always have to look at the states. So let's look at this and see if we can figure out what our states would be. So our gases are H2 and O2 are both gases at room temperature, and water is a liquid. Okay, now we don't include solids or liquids, so that means that H2 that we put in there before really shouldn't be there because it is a liquid. So we'll go back and just erase it. All right. But we can't just have nothing up top, so we just put a 1. All right, so it would be our KEQ is actually equal to 1 over H2 squared times O2. All right, your K value is really nice, and we care about it because it's constant for given temperatures. If you change your temperature, your K value will change depending, and it might get bigger or smaller depending on if your reaction is exothermic or endothermic. But generally, your K value is going to, or always your K value is going to be constant unless you change your temperature, and it's going to give you a really good indication of which side is going to be favored. All right. So let's try this guy. It says we've got this reaction. We want to determine the equilibrium expression for this guy. All right, so we'll say our KEQ. All right, did I remember to move my face? I did. I'm so smart. So our KEQ, we do products over reactants. These are our products, so it would be the concentration of SO3 squared over the concentration of SO2 squared times the concentration of O2. And then we double check to make sure we didn't have any solids or liquids, gas, 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 so we're good. So that's our equilibrium expression. So that's the answer to that first bullet point. Second bullet point is to determine the value of the equilibrium constant given those equilibrium values. All right. So we're going to say here's our equilibrium values. Notice that they're in brackets right here, so we know that they're already in concentration, so we don't have to divide by the volume. If you're given moles in a volume, you got to make sure you convert it into concentration. That's an easy thing to forget. So let's see. So we do SO3, so that's the 3.50. We square that guy. And then SO2 squared, so that's 1.50. And we're going to square that guy times O2, which is 1.25. All right, and let's see what happened. We have 3.5 squared divided by 1.5 squared times 0.25. All right, so you should get 4.36. All right, make sure one thing that I see students mess up on is they forget that this whole thing needs to be in parentheses down here. If you don't put that in parentheses, your calculator will take 3.5 squared and then divide it by 1.5 squared and then multiply that answer by 1.25. All right, so your answer is 4.36. Now, what does this value indicate about the equilibrium? Well, let's think about our equilibrium constant real quick. Or one side note, let's talk about this real quick. It's really, really common, these type of questions, that you'll have your equilibrium expression, you'll be able to write that, but then it'll ask you, well, calculate if this is your K value, right, and it'll give you a K value, calculate the concentration of one of your reactants or products. And so essentially that would turn into an algebra problem. So say it asks you to calculate the concentration of SO3, and you would take your K value and you'd be like, well, 4.36 is equal to, and since you're calculating SO3, that would be the x squared divided by it, and it would give you two values for these guys, and so you'd plug those values in, and then you just solve for x. So essentially, if you get a problem where it asks you to calculate something other than k, all you have to do is rearrange it to solve for that thing. All right. Now let's take a step back here. It says, what does this value indicate? So we just calculated our KEQ value, and we want to know what does this value indicate about the equilibrium? Well, let's think about K. All right, our KEQ is equal, remember it's equal to the concentration of the products divided by the concentration of the reactants. All right, so the concentration of the products over the reactants. So essentially what this is it tells us the ratio of the products to the reactants. So if our products are bigger than our reactants, then we should get a rather large K, right? Because our numerator was bigger than our denominator. If the reactants are more concentrated than the products, then we'll get a small K, all right? So because this number is bigger than 1, we know our products are favored because the product value, that numerator, was bigger than the denominator. All right, and so this we call this the equilibrium position. All right, and that equilibrium position tells us whether the reactants or products are favored. All right, so that's what we call that, the favored. Does it lie to the left or lie to the right? All right, if it's a reactant favored, we say it lies to the left. If it's product favored, we say it lies to the right. All right, so here's A going to B. Okay, it says if at equilibrium there is significantly more B than A, then we say it is forward favored. All right, so if B is more than A, then our KEQ would be greater than 1 because our products are bigger than our reactants. All right, and so we say so these two are paired up. Forward favored and product favored mean the same thing. We could also say reverse favored down here. Reversed. Why are you doing this to me? Reverse favored. Okay, or reactants are favored, right? Those mean the same thing. You could also see it written kind of like this here, where you've got like a big arrow pointing towards the direction it's favored. So in this particular case, notice that A is 95% and B is only 5%. And so this arrow gives us an indication of which side is favored. All right, so that's it for part 1. Some new ideas about equilibrium. We talked about equilibrium expression and getting some information from K. Equilibrium in chemistry can get really complicated pretty fast, so make sure you get these basic ideas down pat so that as we move forward, you can kind of keep building on that expertise. All right, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.